Good day, grade 12s. Hope you're doing well. Today we are looking at special cases with cubic functions. So you know now how to do the various calculations, but now we're looking at special cases. The first one I want to look at is this one. Fx equals x cubed. Okay. So this one has a very specific graph. I've showed you this one previously with a previous video, but I'm going to show you what typically will happen in a test. Okay, so especially when you're working fast and you may be a little bit stressed and stuff like that. So now you are going to look at this. You're going to say, okay, oh my goodness, I don't know what to do. What's the first thing you need to do? Get the y-intercept. Now you can clearly see if x becomes 0, to get the y-intercept, you'll just get a 0. So y-intercept is equal to 0. And then you're going to make your y 0 to get an x. So it's x cubed equals to 0. So that will tell you the x-intercept is also equal to 0. Okay, so now you know the x and the y-intercept is at 0. Now the next step is probably to get the first derivative. And you will see it becomes a 3x squared. And you're going to make that 0 to get to the turning point. So then it's 0 equals 3x squared. That tells me x is yet again 0. Then you're going to get the second derivative, which is 6x in this case. And you're going to make this 0 as well to get your point of inflection, right? And yet again you get it as equal to 0. So your y-intercept, your x-intercept, your turning points, and your point of inflection is all of them are at 0. Okay, and this is why. To the right hand side it looks like half of a parabola, and to the left hand side as well, but just the concavity is opposite. Okay, and you can see that over here, that with the second derivative being equal to 6x, make x a positive value, it will be positively concave, like that part. Make x a negative value, this will be negative, that means negatively concave, like this. So this is the one special case that we have. The second special case that I want to look at is the following. Negative x cubed. Remember, whenever a function just becomes negative, that means the whole thing became negative. It was rotated around the x-axis. So if you have a look at this graph now, this part will go down and that part will go up. And that's it. That's the graph. So, and you can test it as well. For any positive x value times a negative will become a negative. Any negative x value cubed will become a negative times a negative is a positive. Okay. So, and the same over there. Any negative value cubed is negative. Any positive value cubed is positive. Okay, now I would like to look at another special case. So let's say, for instance, you have something that looks like this. Negative x cubed plus 3x minus 2. Okay, so first things first is you need to get a factor so that you can do long division or synthetic division. Now if you quickly test, you see that's a negative 1 plus 3 negative 2 is equal to 0. That means that 1, x equals 1, is a factor, right? Okay, now from here on we do our synthetic division. So we have negative 1. Remember the x squared is a 0. And that is a 1. We're just going to put it right there. 0 there. So this is negative 1. 1 times negative 1 is negative 1. 0 plus a negative 1 is negative 1. 1 times a negative 1 is negative 1. 3 plus a negative 1 is 2. 1 times 2 is 2. Those two add together to be 0. That's our remainder, right? So what do we have here? Is we have negative x squared minus x plus 2. Remember we started off with it being equal to 0, right? We made y 0 so we can get the factors. So if we work from here, we can multiply with a negative 1 on both sides. And then factorize. Okay, so this then means that negative x cube plus 3x minus 2 is equal to, from the first factor, right, x equals 1, that means x minus 1 is a solution, so x minus 1 is a factor, so it's x minus 1 times x plus 2 times x minus 1. And now you see that we've got two roots that's exactly the same. The moment you see that, you know that the turning point is on the x-axis. That's immediately what you can get from this. Okay, so when you draw this graph, it's going to look like this, with this turning point being at 1 and that intercept at -2. And let's quickly just confirm this by taking the first derivative. So from here, here's the original function. We take the first derivative, it becomes minus 3x squared plus 3. We make the first derivative equal to 0. That means 0 equals negative 3x squared plus 3. Okay, now we just need to solve. So negative 3 equals negative 3x squared. So you divide, it becomes a 1. So that means x equals plus 1 or negative 1, right? And now, if we look at our graph, you can see that the one turning point is at 1, the other one is at -1. And so that just confirms again what I've just mentioned. The next one I want to look at is, let's say, something like this: 3x cubed plus 2x squared plus 4x. Just like that, without an added constant right there. Okay, so whenever you see this, you immediately know the y-intercept is 0. Okay, and secondly, if we want to get the x-intercept, when we make the function equal to 0, your very first step is to factorize by taking out an x, right? So then it becomes 3x squared plus 2x plus 4. Okay, so immediately you know x equal to 0. This is one of your factors. And then you can get the other two through factorization. So then your graph will look something like this, with your one factor on the 0 and the other two factors on the same side. Okay, in this case, it doesn't have to be on the same side always. It just means one of the factors will be 0. Like I said, it could have looked like this as well. It could have even looked like that. All of that depends on the rest of the function. Okay, so just to show you, that's another case. The moment you see no constant there, meaning it's a plus 0, right? Then you know it's going to look something like this. Okay, and finally we're going to talk about the presentation of information. Okay, so let me draw a cubic function, and you will see a similar graph on page 188 in your textbooks. Okay, so, and I would love to talk you through this. Okay, let me just move the y-axis a little bit. So this is function f, a normal cubic function. Okay, and I want to show you how information can be presented in a question. Okay, so let's take it through. So here the gradient is positive till the turning point where the gradient is 0. Then the gradient is negative until the turning point, and it's 0 again, and it's positive again. Okay, but before we go on, let's just write down a hypothetical cubic function. There we go. So from here on, we can get the first derivative. 3x squared plus 6x plus 4. And from there on we can get the second derivative, 6x plus 6 in this case. Okay. This is a cubic function. You can clearly see that the first derivative is a positive parabola, and the second derivative is a straight line. Okay, keep that in mind, and it will be confirmed when we look at the graph now. Okay, what's the first thing we do when we want to get the turning points? We get the first derivative. After we've got the first derivative, we make it equal to 0, right? So because at the turning point, the gradient is 0. The two turning points, right? Local maximum, local minimum. So these are also called stationary points, remember that, right? So at this point, if we want to draw the first derivative will be 0 over there and over there. Remember, the first derivative represents the gradient of the graph, right? So here the gradient is positive until 0. That means it would be above the x-axis until that point, right? And then over here, it is negative until 0 again, so it will be below the x-axis, and over here it's positive from here onwards, right? So this graph will look something like this, and it's the first derivative's representation. Okay, so I'm just going to again show you. Here is where the gradient of the cubic function is 0. That means the first derivative is 0. Here it's also 0 because the turning point, right? The gradient is again 0. In between, the gradient is negative, so that means it has to be negative. To the left, it's a positive gradient, so it has to be above the line. To the right, it's a positive gradient, it has to be above the line. So when they give you the graph, they tell you, this is the graph of the first derivative. You know the first thing you're going to look at is where are the intercepts of that graph, because that would be the x coordinates of the turning points. Okay. The second thing you need to look at is it's a turning point right there. The first derivative's turning point. Okay. Now, when we take the first derivative and we get the second derivative from there, we make it equal to 0 to get the point of inflection, right? So right over here, where the first derivative is equal to 0, the second derivative is equal to 0, that means the first derivative's turning point. This corresponds with the point of inflection. So if they give you the graph of the first derivative, you can get three things. You can get the x coordinate of the two turning points, right? And the x coordinate of the point of inflection. Now, if you want to draw the second derivative's graph, it will have an x-intercept right over there, right at the same point. And in this case, you ask yourself, to the left, is this graph concave upwards or downwards? Meaning, is it positively concave or negatively concave? And you will see it's negatively concave. So the second derivative has to be below the x-axis, right? To the right, is it positively concave or negative? It is positively concave. So the second derivative's graph will look like this. So if you get the second derivative's graph and you have to deduce information from there, you can get the point of inflection's x coordinate and where is it negatively concave and positively concave. You get the first derivative, you can get the turning points of the cubic function and the point of inflection. You can technically get the concavity as well, you know, how it changes. Okay, so it's positive gradient to negative gradient, that means it does this, so it's concave downward. Negative to positive is the other way around, so you can get information from there. So this is how it works together.